July 14, 1943, 11:47 a.m. Soviet metallurgist Viktor Markov stared in disbelief at the samples before him. His laboratory in Chelyabinsk had just analyzed the first armor plates from a captured German Tiger tank. The measurement read 300 Brinell hardness. Impossible. Soviet armor peaked at 240 Brinell. The German engineers had developed a metallurgical process the Soviet Union simply didn't understand. Markov knew the Red Army was technologically 5 years behind. The Tiger's 110mm thick frontal armor wasn't just thicker, it was fundamentally different. Henschel and Krupp had perfected a cementation technique that hardened the outer 25mm of the armor plate to extreme hardness, while the interior remained ductile and shatter-resistant. German precision manufacturing made Soviet metallurgy look primitive. Each armor plate underwent a 3-stage hardening process at exactly controlled temperatures: 1562 degrees Fahrenheit heating, oil bath quenching, 968 degrees Fahrenheit tempering. Deviations of more than 9 degrees Fahrenheit destroyed the desired metallurgical properties. Markov had been analyzing Soviet T-34 tank armor since 1941. He knew every compromise, every weakness, every production bottleneck. Soviet steel mills could produce homogeneous armor plates with acceptable hardness. But what the Germans had achieved wasn't an improvement on existing technology. It was a complete re-engineering based on precision control that Soviet mass production could not replicate. The Tiger's armor represented German engineering at its peak. The technical report Markov sent to the People's Commissariat of Tank Production described the reality without embellishment. Tiger armor resisted Soviet 76.2mm shells at all relevant combat ranges. The hardened outer layer shattered Soviet armor-piercing rounds on impact. The ductile inner layer prevented spalling. German metallurgists had solved the fundamental problem that Soviet engineers had been frustrated by for years: how to combine extreme hardness with structural integrity. But how had the Germans achieved this superiority? The answer lay with Krupp Industries in Essen. Since 1934, Krupp had invested massively in metallurgical research. German engineers, under the leadership of Dr. William Rowland, systematically developed cementation processes for tank steel. They tested hundreds of alloy combinations: 0.42% carbon, 1.65% nickel, 1.58% chromium, 0.95% molybdenum. Each variation was tested under controlled conditions: shelling tests with various calibers, hardness measurements at dozens of points per plate, microscopic analysis of the grain structure. German precision meant measurable, repeatable superiority. Soviet tank production was based on completely different priorities. Stalin demanded quantity. Soviet steel mills in Magnitogorsk and Chelyabinsk produced armor plates as fast as the blast furnaces could spew steel. Quality control meant visual inspection for obvious defects, hardness measurements on sample batches, no systematic metallurgical optimization. Soviet T-34 armor showed massive hardness variation within the same plate, 180 to 240 Brinell, depending on cooling rate and local steel composition. German Tiger armor showed hardness variation of less than 10 Brinell across the entire plate. This consistency was no accident. Henschel developed specialized hardening furnaces with precise temperature control. Each 110mm armor plate was individually heated for over 6 hours, monitored by thermocouples at 12 different points. Quenching occurred in temperature-controlled oil baths, with exactly defined flow rates. Tempering used induction heating for uniform temperature distribution. German engineering meant processes that Soviet mass production could not approximate. The first confrontation between Soviet tanks and Tiger armor came in January 1943 near Leningrad. Soviet 76.2 mm guns fired on Tigers from 800 meters. The shells bounced off or shattered on impact. Soviet tank commanders reported bright sparks when shells struck the Tiger's frontal armor. No penetration, no damage. The 110 mm Krupp armor made the Tiger practically invulnerable from the front. Soviet intelligence reports from this time described the Tiger's armor with terms that betrayed technical AWE. A report from March 1943 to Stalin personally analyzed captured armor samples. The German armor plates demonstrate metallurgical superiority that our current production methods cannot achieve. The outer hardened layer achieves hardnesses that cause our shells to shatter. Recommendation: immediate development of new penetration ammunition and systematic study of German metallurgy processes. Viktor Markov received instructions to replicate German armor technology. He understood the magnitude of this task. German Krupp cementation required more than just knowledge of temperatures and alloys. It required precision equipment that the Soviet Union did not possess. Temperature control systems with accuracy of plus or minus 5 degrees Fahrenheit. Oil baths with exact chemical composition for optimal quenching rate. Induction heating for precise tempering. Hardness testing equipment calibrated to 2 Brinell accuracy. Each element was its own technological challenge. Soviet attempts to copy Tiger armor began in August 1943. The Chelyabinsk tank plant received instructions to produce experimental plates based on the German model. The first attempts failed completely. Soviet blast furnaces could not maintain the required temperature control. The cementation was uneven. The hardness varied from 200 to 280 Brinell on the same plate. Shelling tests showed that Soviet reproductions were barely better than standard T-34 armor. Soviet metallurgy faced a systemic problem. German precision wasn't just a matter of better engineers. It was a matter of industrial culture. Krupp had 80 years of experience in precision steel manufacturing. German workers were trained in apprenticeship programs that lasted 4 years. Quality control was integrated into every production step. Soviet steel mills had accelerated from peasant economy to mass production in 10 years. Workers had weeks of training instead of years. Quality control was after-the-fact inspection instead of preventative process control. But the Soviet Union had one resource that Germany lacked: captured Tiger tanks. In the summer of 1943, the Red Army captured several Tigers at Kursk. These tanks were systematically dismantled. Every armor plate was measured, weighed, and analyzed. Soviet metallurgists conducted hundreds of tests, hardness measurements at dozens of points, spectroscopic analysis of the alloy composition, microscopic examination of the grain structure, impact resistance tests at various temperatures. The Germans had left behind a blueprint. The Soviets just needed to learn how to read it. Dr. Afanasy Zavyalov, lead metallurgist for the IS heavy tank program, was given the responsibility of bringing Soviet armor up to German standards. Zavyalov understood that complete replication was impossible. Soviet industry couldn't produce the precision equipment that German Krupp Industries cementation required. But Zavyalov could adapt the basic metallurgical principles: higher nickel and chromium content for better hardenability, controlled cooling even without precise oil baths, surface cementation through longer heating at moderate temperatures instead of short heating at precision temperatures. The IS-2 heavy tank, which entered production in late 1943, represented the Soviet adaptation of German technology. The front armor was 110 millimeters thick, identical to the Tiger. The hardness reached 260 to 280 Brinell, significantly better than previous Soviet armor, but still below German consistency. Cementation was present but less pronounced. Soviet engineers hadn't copied the German solution. They had developed a Soviet approach that was feasible with available resources, but the IS-2 armor showed that the Soviets understood German principles. Later, IS-3 tanks, developed in 1944, used improved cementation processes that were closer to German quality. Soviet steel plants invested in better temperature control. Metallurgists developed optimized alloys for available production methods. The Red Army couldn't achieve German precision, but they had learned to work with 90% of German quality. In a war of mass production, 90% quality at twice the quantity was a winning strategy. The true irony of the story came after the war. Operation Osoaviakhim in October 1946 deported thousands of German engineers and technicians to the Soviet Union. Krupp Industries metallurgists, Henschel production specialists, Germans with decades of experience in precision steel manufacturing. These Germans were forced to work in Soviet design bureaus and factories. They brought not only knowledge, but working methods, quality standards, problem-solving approaches. German engineering became Soviet state property. The T-10 heavy tank, a Soviet post-war development of the IS series, used armor technology developed directly by German prisoner-of-war engineers. 120mm front armor with full Krupp-style cementation, hardness of 290 to 310, Brunel with variation under 15 Brunel. The Soviets had finally achieved the precision that the Germans had demonstrated in 1943. It had taken German engineers working under Soviet direction to bring Soviet armor up to German levels. Viktor Markov, who had analyzed the first Tiger tank armor in 1943, worked with former Krupp Industries engineers in the 1950s. In an interview after the collapse of the Soviet Union in 1992, he described the experience. The German engineers thought differently than we did. For them, quality wasn't something you checked after production. Quality was something you built into the process. They insisted on measurements, controls, standards for every step. At first I thought it was just German perfectionism. Later I understood that was German engineering. Without their methods, we would never have brought Soviet armor up to world-class levels. The Tiger tank armor didn't just influence Soviet tanks. American and British intelligence reports analyzed German armor technology with the same awe. A British metallurgy report from July 1944 about captured Tiger components noted German cementation processes achieve hardness layers that our current production methods cannot replicate. The combination of surface hardness and core toughness shows advanced understanding of heat treatment technology. Recommendation: detailed study of German procedures for post-war application. This recommendation became reality. Post-war NATO armor used cementation processes that were directly derived from German Krupp Industries methods. The American M60 Patton tank used hardened armor plates with hardness over 300 Brunel, achieved through processes that German prisoner-of-war metallurgists adapted for American steel plants. The British Chieftain tank used similar technology, developed with the help of Vickers Armstrong engineers who had studied German methods. Modern armor is more complex. Composite materials, ceramics, reactive armor have supplemented or replaced homogeneous steel, but the metallurgical foundations that German engineers demonstrated in 1943 remain relevant. The American M1 Abrams uses hardened steel in its composite armor. The hardening processes come directly from Krupp cementation methods. The German Leopard 2 uses advanced steel alloys, developed by companies that are successors to Krupp Industries. The technological lineage from the 1943 Tiger to 2020's armor is directly traceable. The Tiger tank armor was more than military hardware. It was a demonstrator of German precision manufacturing, the ability to achieve consistent quality in mass production. the integration of material science, production engineering, and quality control. These capabilities defined German industry before the war. The Tiger showed that even under wartime conditions, German precision remained. That was the lesson that Soviet, American and British engineers learned. German engineering wasn't propaganda. It was measurable technical superiority. Today, metallurgy programs worldwide teach hardening processes using examples that go directly back to German wartime developments. Krupp cementation is a standard topic in courses on heat treatment. Students learn about surface hardening versus core properties using Tiger tank armor as a historical example. German engineers who developed this technology are long dead, but their methods live on in every modern steel production facility. The story of Tiger tank armor is the story of how technological superiority defined post-war development. The Soviets didn't just copy armor plates. They copied metallurgical processes, quality standards, production methods. This act of replication defined Soviet heavy tanks for the next 40 years. The IS-2, the IS-3, the T-10, all bore the mark of German metallurgy. Every 110mm armor plate was a reminder. German steel set the standard the world was trying to reach. The production reality behind the Tiger tank armor revealed even more dimensions of German precision. Each 110mm armor plate weighed 1,515 pounds. Manufacturing just one plate required 43 labor hours, 8 hours rolling the raw steel, 12 hours of controlled heating, 6 hours of quenching and stabilization, 9 hours of tempering, and 8 hours of quality control and finishing. Henschel produced a maximum of 8 complete armor sets per day. Each Tiger required 23 large armor plates, plus 47 smaller components. German quality meant limited quantity. Soviet tank production operated on entirely different principles. The Chelyabinsk tractor plant, converted into a tank factory in 1941, produced T-34 tank armor in mass quantities. An armor plate required just 6 labor hours from raw steel to finished product. Quality control meant visual inspection and spot hardness tests. The plant produced 120 T-34s per day at peak production. Soviet quantity overwhelmed German quality through sheer numbers, but the Soviets knew their armor was inferior. The question was how to close that gap without accepting German production times. The solution came through adaptation, not replication. Soviet metallurgists under Dr. Zavyalov developed modified cementation processes that delivered 70% of German quality, with 150% of Soviet production speed. Instead of 12 hours of precise heating, they used 8 hours at a slightly lower temperature. Instead of controlled oil bath quenching, they used air quenching with a water spray mist. Instead of induction tempering, they used conventional furnace tempering. The result, IS-2 armor with 260 to 280 Brinell hardness, produced in 18 hours per plate. Not German perfect, but 40% better than earlier Soviet armor. This pragmatic engineering defined the Soviet approach to technology. The Soviets didn't simply copy German solutions, they copied German principles and adapted them for Soviet reality. The result was good enough to win the war, even if it wasn't good enough to reach German standards. Post-war development with German engineers then brought Soviet processes up to German levels. The metallurgical archives of the Soviet Union, accessible after 1991, revealed the depth of German influence. Production manuals for T-10 armor from the 1950s are practically translations of German Krupp Industries documents, temperature curves, quenching rates, tempering schedules, hardness testing protocols, all follow German standards with minimal adaptation. Soviet metallurgists hadn't just adopted German technology, they had adopted German methodology, the way to think about material science, the precision in process control, the systematic approach to quality assurance. The global influence was even more comprehensive. British armour for the Centurion used similar cementation methods, developed by studying captured German documents. American M48 Patton armour used processes directly adapted from German prisoner-of-war metallurgists working for Bethlehem Steel. French AMX-50 armour used technology based on German methods that French engineers studied in occupied German factories. The 110mm Tiger armour set a global standard that every tank-building nation tried to reach. Modern tank steel production is a direct successor to these wartime developments. Rheinmetall, successor to parts of Krupp Industries, produces armour for the Leopard 2, with methods that are an evolutionary advancement of 1943 processes. The temperatures are more precise, the alloys are more complex, the quality control is automated, but the fundamental metallurgical principles that Krupp Industries engineers developed remain recognizable: hardened surface, tough core, precise process control, systematic quality assurance. The story of Tiger tank armor is also the story of Operation Paperclip and the Soviet equivalent, Osoaviakim. Both Allied powers realized German engineers were more valuable than German territory. The USA deported 1,600 German scientists and engineers after the war. The Soviet Union deported an estimated 2,200 German specialists. Many were metallurgists, chemists, production engineers who had worked on armor development. These men brought more than just knowledge. They brought 20 years of experience in precision manufacturing. Dr. William Rowland, the Krupp Industries metallurgist who had perfected the cementation process, worked for the US Army Ordnance after the war. He developed armor processes for the M60 Patton. His work flowed directly into American military standards. Dr. Henry Galen, a Henschel production engineer, worked for Soviet tank factories from 1946 to 1952. He trained a generation of Soviet engineers in German precision methods. The Tiger armor didn't win the war for Germany, but German armor engineers won the peace for their captors. The economic implications were massive. The Soviet Union invested an estimated 480 million rubles in armor improvement between 1943 and 1955, largely based on German technology. The USA invested $180 million in improved armor between 1945 and 1960. Again, primarily based on German methods and German engineers. Great Britain invested £45 million. All three programs returned to the same source: Krupp Industries metallurgy and Henschel production. German engineering became global intellectual property, stolen, but no less valuable. These technologies are not just history. They are the foundation of modern materials science, from automobile steel to aircraft alloys, from tool steel to construction beams. The principles that Krupp Industries developed for Tiger armor are now industrial standards. Hardened surfaces for wear resistance, a tough core for structural integrity, precise temperature control for consistent properties, systematic quality testing. German wartime engineers laid the metallurgical foundations upon which modern industry is built. The Tiger armor was also a catalyst for metallurgical research worldwide. Post-war universities established specialized programs in heat treatment and surface hardening, inspired by German war technology. The MIT Materials Science program, founded in 1946, used Tiger tank armor as a case study in its very first courses. The Technical University of Berlin, rebuilt after the war, made Krupp cementation a core part of the curriculum for metallurgy students. Moscow State University of Steel and Alloys taught German hardening methods as standard industrial practice. Victor Markov, who analyzed that first Tiger tank armor in 1943, became a professor of metallurgy at Chelyabinsk University in 1955. His textbooks on heat treatment, written in the 1960s, are practically translations of German Krupp handbooks, filled with Soviet examples. 3 generations of Soviet metallurgists learned German precision through Markov's teachings. He died in 1989, just 2 years before the collapse of the Soviet Union. His last article, published posthumously in 1990, was titled German Metallurgy as the Foundation of Soviet Armor Technology, a Historical Analysis. The article was Markov's confession: without German technology, the Soviet Union would never have achieved world-class armor. The Germans themselves reflected differently on post-war technology transfer. Dr. William Rowland, who worked for the US Army, saw it pragmatically. Technology belongs to humanity. The war brought destruction. At least it also brought technological progress for all nations. Dr. Henry Galen, who worked for the Soviets, was more bitter. We were treated like spoils of war. Our work, our knowledge, simply stolen without compensation or recognition. But he conceded. The Soviets learned quickly. They had respect for German methods, even if they showed no respect for German people. These differing perspectives reflect the complexity of technological superiority. In a political context, Tiger tank armor was German intellectual property developed through years of German research and investment. But after military defeat, this property became international common knowledge, copied by the victors without licensing or payment. Was that theft or legitimate spoils of war? The answer depends on who you ask. German engineers saw it as robbery. Allied governments saw it as reparations. Historians today see it as an inevitable technology transfer after total military defeat. Regardless of ethical questions, the technical reality remains. German armor technology defined post-war development for 40 years. Every Soviet heavy tank, until the collapse of the USSR, used metallurgical principles based on Krupp methods. Every NATO tank, until the introduction of composite armor, used similar German hardening processes. Modern Leopard 2 and M1 Abrams tanks use advanced materials, but the steel components are manufactured with methods that are evolutionary successors of 1943 Krupp cementation. The Chinese People's Liberation Army, which copied Soviet T-54 and T-55 tanks, thereby indirectly copied German armor technology. Chinese Type 59 tanks used armor manufactured according to Soviet standards, which were based on German methods. North Korean tanks used the same technology lineage. Indian tanks, based on Soviet designs, continued the tradition. German Tiger tank armor from 1943 had a global influence on tank construction. Well into the 1990s, 3 generations after its original development. Today, material scientists are working on nano-structured armor, on ceramic composites, on reactive armor. But when these scientists study surface hardening, they start with Krupp cementation. When they analyze temperature control, they reference German war processes. When they talk about quality standards, they refer to Henschel precision. Modern materials, science has surpassed Tiger tank armor, but it has not forgotten it. German engineering from 1943 remains a reference point for what precision manufacturing can achieve. These stories are not just archival documents, they are living connections between past and present. The technology in your car, the precision in your tools, the quality standards in your industry. All bear traces of German wartime development. If you value these technical truths, if you understand that history is not just events, but technology, support with YouTube, super thanks. Every super thanks enables deeper archival research, digitization of rare documents, interviews with the last living engineers who experienced these technologies. Help preserve this technical history before the last generation who can witness it disappears. The 110mm Tiger tank armor was more than military hardware. It was a manifesto of German precision. It was proof that technical excellence is measurable, repeatable, verifiable. The Soviets learned this lesson in 1943 and spent 40 years trying to replicate it. The world is still learning this lesson today. German engineering sets standards that endure for generations. Every modern armor plate, every hardened component, every precision-manufactured steel part carries the legacy of Krupp, Henschel, and the German metallurgists, who showed in 1943 what technical superiority means. Which German armor technology was more revolutionary? Tiger tank armor or Panther sloped armor? Technicians and engineers in the comments have shared incredible analyses. Grandfathers who worked at Krupp, company documents on post-war licensing, modern steel mills that still use Krupp methods. Share your technical discoveries. Every comment is a piece of the technical history puzzle.